Good morning. Good morning, everyone. Today in time. Good morning. I will write this. About the lecture halls. So supposed to be lecture hall number 2 for all lectures, but something like psychology today's morning happened. I don't know why it appears. So supposed to be lecture hall number 2 for biology, for chemistry, but for psychology as well. No, but if something different, I will try to inform you before, even morning time. Okay, so today's topic, solutions and colligative properties of solutions. So solution is something we deal in with the most often. According to the, let us say, according to the composition, according to the nature of substance dissolved, according to the behavior of solution, there can be homogeneous and heterogeneous. But now we will deal with liquid solutions mainly and solutions of homogeneous nature. So what are solutions? Homogeneous mixture of two or more pure substances. Definitely, if we deal with the true solutions, they are homogeneous, which composition may be varied within certain limits. What does it mean? That means concentration of dissolved substance can be different within exact limits. Components of solutions are solvent and solute. Usually one solvent. Solvent is a medium where solute dissolved. According to the common classification, according to the common naming of composition of solution, usually instead of solvent we use dispersion medium. Instead of solute, dispersed phase. But for true solutions, word solvent and word solute, acceptable and even recommended. For solution to be homogeneous according to the nature, supposed to be diameter of solute particle less than 1 nanometer. Want to remind you that 10 power negative 9 meter, it's a 1 nanometer less. In such case, it's a homogeneous medium. How to decide which one solvent, which one solute is? Again, we will discuss today in a lecture only water, not aqueous mainly, but liquid solutions. Solvent, it's the same substance, same aggregate state, same physical state as a solution itself, because of its a medium. So if we see that solution is liquid, we can be sure that solvent is liquid or substance as well. Solute dissolved there can be gas, can be liquid, can be solid. According to this, all solutions can be classified into 3 types. Well, first of all, according to how they look like, aggregate state. So if they are both are solids, both solvent and solute. Alloys, for example, chromium nickel, it's a mixture 80 to 20%, very heat resistant one. So we applied in industry. So what we can say about how to decide which one solute, which one solvent is. The one with the highest value, the biggest concentration one, it's a medium. The smaller one, it's a solute. So in this case, as chromium and nickel can be different percentage, due to this can be one solvent, can be a second one. If they're 80 to 20, that means 80 chromium, 20 nickel, or 80 nickel, 20 chromium, the most often. That's why nickel is a solvent. Liquid, according to aggregate state solution, means that solvent supposed to be liquid. It's easy to decide. One exception is water. Even if less water, water is a solvent. For example, if we mix two liquids, alcohol like ethanol, for example, and water, even if there will be 90% of alcohol and 10% of water, it's still aqueous solution of alcohol, but not alcohol solution of water. Greater amount one, a water exception. No, for gases, mixture of gases, any one, for example, gas anesthesia, more often we use laughing gas and oxygen, 50-50%, but there can be ether present, no, and the medium is air. Air here, higher concentration, that's why it will be solvent, but if they're 50-50%, no, it's our choice. Oxygen, usually we're saying it's a medium. So what about solutions we need to know? Well, today, as I told you, we will discuss aqueous solution. That means water is a solvent there. I will not put a lot of attention to the water nature because of you should know this. I want to just remind you that it's a unique solvent. Unique because of the presence of hydrogen bonds, stabilizing, forming aggregates in a solid state and in liquid medium. What is aggregate state? I hope you know. It's what is hydrogen bond? I hope you know. It's a weak bond, quite weak, maximum 20 kilojoule per mole energy. Bond energy, it's energy needs to be used to destroy the bond. So that's why it's a weak, but there are a lot of hydrogen bonds and they even change the physical state of the water. According to the position, according to the place in periodic table, oxygen place, H2O supposed to be gas, as H2S, lower in periodic table element, it's a gas. Water is supposed to be gas, but it's a liquid. And the reason is formation of associates. As well as water, it has abnormal high boiling point, and it has unique structure because of electronegativity of the oxygen. It's dipolar structure. Oxygen attract electron density, not completely, it's not a unique compound. They're covalent polar bond, but oxygen minus delta charge and hydrogen part is plus delta charged. Angle, it's not 108, it's a little bit different because of lone pairs, and it's short of 104.5. So it's a dipole. That's why it's a great solvent to stabilize polar compounds and ionic in an aqueous medium, to dissolve them. According to the molecular weight of the solute, all solutions can be classified into low molecular and high molecular, known as polymers. If molecular mass, molecular weight less than 5,000 gram per mole, they behave different way. Molecular mass is quite low. Usually we deal with a solution with much lower than 5,000 in organic salts, acids, bases. They follow this rule and they give a set of properties. We will discuss them. Higher molecular weight compounds, because of their higher molecular mass, their size is much bigger. The size is bigger than 1 nanometer because of the weight. And that's why higher molecular weight compounds, they follow other rules and they are close according to their behavior to colloidal solutions because of the size higher than 1 nanometer. They already can be accepted as a heterogeneous, but they are dissolves. They are soluble can be. So it's a second classification, and third one, everyone's know. I just want to remind you, it's a classification according to the conductivity. There can be solutions of electrolytes and solutions of non-electrolytes. Electrolytes are substances when they dissolve in an aqueous, they dissociate into ions, and that's why conducting electric current. It's not correct to say that because of electric current they dissolve. No, they dissociate into ions, and that's why conduct electricity. Here can be salts, acid, bases as examples. Some of the electrolytes strong, some of them weak, some medial strong. Due to this, they can dissociate completely, can dissociate partially, but they all conduct electricity. Non-electrolytes, even being very well soluble in water or other solvents, they are never dissociated. And that's why I don't conduct an electric current. Conductivity of this solution, same as conductivity of solvent. So, to understand the behavior of solution, necessary to compare solutions with mixtures. Some think there are no difference. So what we mix solute, we mix with a solvent, and they should behave as a solvent and solute do. But if we're dealing with a mixture just, it's truth. Properties, mixtures follow same rules, their components follow. So that means they give a set of properties typical for one component and for second independent, but nothing extra. Solutions accept properties of solvent and solute. They have extra properties because of their chemical reaction happen. Between solute and solvent, their chemical reactions. For mixtures, just no. For solution, yes. And it can be proved because of unique new properties appears. As example, everywhere mentioned copper sulfate, which is white ionic crystalline, ionic solid. When we dissolve in water, solution becomes blue. As well as if we will use evaporation. The first step of evaporation is formation of crystallohydrates. Copper sulfate times 5 molecules of water. It's also blue. So it's a provement that copper sulfate, when dissolves, it's a chemically react with the water. Formation of hydrates there happen. And the second provement of this, that chemical reaction, their heat effects are present. We know that if there are any change in a structure, there are supposed to be changes in heat contents as internal energy changes. And if it's so, heat effect must be there. No heat effect, that means no chemical reaction. When substance is dissolved, we can observe exo or endothermic. So second step of this theory of solution is that dissolution, that solution is reversible process. It's possible to shift the equilibrium. And heat effect, final heat effect of solution depends on two factors. First one, it's the energy of the lattice, the crystalline energy. What is the energy? Its energy needs to be used to destroy the bond, to destroy this crystalline lattice. It's always endothermic. Always heat should be absorbed from surrounding to destroy the structure, the crystalline structure. And then hydration happens. Water attached to these particles present in lattice. It can be ionic, it can be molecular structure, and it's always exo. So due to which one bigger? Is it crystalline structure too strong and hydration can't compensate it? There will be endothermic finally. If it's poor molecular crystalline, their hydration will be bigger effect, and that's why finally we will get exothermic, sometimes even strong exothermic, but they are always present, the heat effect. Just for you to remind how the formation of solution happen, here sodium chloride is ionic solid. The ionic structure already there. There are no formation of ionic bond. The ions are present in crystalline structure. Because of water, water helps this structure to be dissolved. The reason is the chemical react. Water helps to destroy there. First of all, bond energy, crystalline lattice energy. It was absorbed, substance dissolved. Water attached to these ions, forming hydrated ions. That's why water present here in a solution into two, even we can say three ways. First one is in hydration, hydrated cations and ions. Hydrated ions, they are at present as a dipole, it's a exact way attract to the plus and minus. Second, destructured water. And far from these hydrated cations and ions, we have still water associates. So substance dissolved, we're talking about solubility. Solubility can be used two different symbols to explain and express, right? It's a capital S, solubility. Capital S symbol. No, so the problem is sometimes students make a mistake where solubility, where entropy is. But it's acceptable, and mostly in a book you can find this. But because of the physical meaning of solubility, then we can use other simply. I will show you that. So solubility is ability of substance to dissolve in a solvent. Some dissolved better, some dissolved worse, some insoluble there. Due to how much, how many, what value of substance dissolved, solutions can be classified into three types. The first is saturated. Saturated solution containing the maximum amount of dissolved substance. That means no more substance can be dissolved. If it's so, that means they are the highest concentration of the substance dissolved in a solution. It's a mathematically this value equal to solubility. No more, it's a maximum. So that's why mathematically solubility equal to the amount of solid that dissolves to give the saturated solution. Now it's clear that unsaturated solution with a less concentration than saturated. And there can be quite unstable situation. We know it's a supersaturated solution, which contains more of solute than saturated solution does. It's quite hard and not for every type of solution possible to prepare supersaturated. It's necessary to prepare saturated first, then increase temperature to form higher temperature unsaturated, and then lower temperature very, very slow without any stressful factor. But they're still unstable. So how this all looks like? Some see no difference between concentrated and saturated solution. It's a big difference because of concentrated or diluted solution. They are both unsaturated. Both unsaturated. Diluted just has very little solute in it. A concentrated has a lot of solute in it. In both of them, more solute can be dissolved. In both diluted and concentrated. But definitely for diluted, more solute can be dissolved than for concentrated. But they are not saturated, unsaturated both. Saturated solution, they are always in equilibrium with precipitate. If we see there are no precipitate, that means it's unsaturated. Because of they're supposed to be equilibrium between solution and crystallization. It's a reversible process, as I mentioned already. So excess of solid always present in precipitate. And that's why above this precipitate, they're the highest, the maximum amount of solute in it. And that's why no more solute can be dissolved. Everything we will add more will goes in the precipitate. So, and as I told you just now, if we will heat careful saturated solution, and this precipitate will be dissolved, then slowing down the temperature very careful way, we can get the room temperature solution with a higher concentration of solid than maximum. This precipitate can still be dissolved, but it's very unstable situation. Again, diluted, concentrated, more solute can be dissolved. That means concentration of substance dissolved. Now I took a sodium chloride, for example. It's a less than solubility value. For saturated solution, concentration of substance dissolved equal to solubility. They are always equilibrium. How to show that our supersaturated solution are unstable? Usually it can be illustrated with dropping of Cs. It's a small crystalline substance, any crystal, small one, piece of something, or we can stir intensively. Because of presence of one extra stressful particle, crystallization of supersaturated solution happen within seconds. It's till saturated solution appears, till saturation. So it's an illustration, it's a picture, show that supersaturated are very, very unstable. There are three factors affecting solubility of substances. First of all, as their chemical reaction happen between solvent and solute, their nature of both important. Nature of solvent and nature of dissolved substance, solute. Now, as you know, I hope that solvent usually 1, but substances dissolved, there can be more than 1, much more. And they can be different nature, like our blood is a solution. There's electrolytes present, non-electrolytes present, and even high molecular weight substances dissolved present. Temperature is a second factor, and the third one, pressure factor, only if their gas is dissolved. So if solute is gas, their pressure effect will be important to understand. So let us see how these factors really affect. Nature is the easiest factor because of their rule like dissolves like. What does it mean? This means polarity of solute and solvent important. It states that polar substances, that means ionic or polar covalent bonded, they have higher tendency to dissolve in a polar solvent. It's not correct to say that polar dissolved polar substances. No, it's about tendency. It's tend to be dissolved. Rather, more often, something like this should be mentioned. Because of we have huge number of ionic substances insoluble in water. We know they are almost insoluble. That's why it's not correct to say like dissolves like, meaning that it's strict law. It's a rule about tend to be. That means, again, polar substances and ionic, they tend to be dissolved. They better dissolve in the polar solvents, and non-polar substances has a tendency to be dissolved in non-polar solvent. As example, always oils and water. Oils is soluble in benzene as non-polar solvent, but insoluble in water, forming two immiscible liquids. So maximum what we can get, oil with water, we can shake vigorously to get emulsion. But emulsion is also unstable and they separate fast enough. Benzene and water also immiscible liquids, so that's why they are not soluble in each other. But sodium chloride in water soluble quite well, but insoluble in benzene, it forms their precipitate. Temperature effect on solubility of gases. There are different temperature effect on solubility of gases in liquids, liquids in liquids, and solid in liquids. Let us see how it's really happened. So as a solubility is reversible process, that's why, as I mentioned already, they are possible to shift the equilibrium. So between gas and solution of the gas, they are equilibrium. As you remember, Le Chatelier's principle state that if they increase in temperature, equilibrium always shifts to the undo the stress, to the endothermic. So that's why for gases, as they are mostly exothermic effect, weak one can be quite weak, almost invisible, but it's exothermic mainly. That's why when we increase the temperature, equilibrium shift backward to undo the stress. And that's why gas solubility decreases with temperature. How can we see this? Boiling water, it's a picture, shows that it's really truth. Why water looks like it's boiled. Bubbles of air dissolved room temperature leaves this water medium because of solubility of gas. They are nitrogen, mainly oxygen. Their solubility decreases with temperature. There are some exceptions present, but this is the main rule. For liquid situation, quite opposite. So let us see the amount of solubility. Just as a picture, carbon dioxide, it's good enough, not good, but better than oxygen, and nitrogen soluble in water. So carbon dioxide, when it dissolved in 100 ml of water, water is density 1, so it's standard temperature, so that's why it's a mass equal to volume. So at 0 Celsius, it's a 0.35 gram. At 15, it's already not 2 times, but almost 2 times lower. That means as lower the temperature, as better gases dissolved there. For liquids, solubility of liquids in liquids increases with temperature because of mainly their exo endothermic effect. But there is some exception of sulfuric acid. Everyone knows there's strong exothermic effect. That's why there will be opposite effect of temperature. But water and sulfuric acid are miscible. That's why we will see no picture illustrate that solubility really decreases with temperature. Mainly there we use this factor if we need to observe, if we need to see due to experiment that solubility really increases with temperature. We're dealing with the partially miscible. What does it mean? Miscible, partially or partly miscible or immiscible. Miscible liquids mean that any volume of substances we can mix, liquid substances now we take, and they are still form homogeneous. As example, alcohol and water, acetic acid and water, sulfuric acid and water. Partially miscible, they are dissolves forming homogeneous till exact concentration. And after this concentration, separation of liquids happen. And then we will see same picture as for immiscible. Two layers. Immiscible means doesn't matter what volume we take, what concentration, there are always two layers. And again, maximum what we can get the emulsion. Some of them can be stabilized, but not so stable. Can be stabilized with the presence of exact substances. We will discuss soon. High molecular weight compounds can stabilize emulsions, but they are always separates. They are immiscible according to their nature because of the, as you see, they're supposed to be opposite polarity, non-polar and polar. What about aniline? Phenol, aniline, what they do? They have benzene ring in a polar group. Lower concentration, they dissolve in a water medium. But after some concentration, their benzene ring becomes higher important than functional group, and they, as a result, their separation happen. How to prove temperature effect using such partially miscible liquids? Room temperature we produce, so we add concentration, we add aniline, for example, to water till separation happens, and then we increase temperature till some temperature. We call it this critical boiling temperature for critical solubility temperature for partially miscible. The solubility increases such way that from two layers again appears homogeneous. That means only here for such substances, for such liquids, we really can see the picture that the solubility of liquids increases with temperature. For miscible, they are always homogeneous. For immiscible, they are always heterogeneous. For partially miscible, it's quite illustrative. So for solid substances, situation not so simple as for previous. For gaseous liquids, they mainly affect exact way, but there are some exceptions. Here we can't say that exception there. We say usually. Usually solubility increases with temperature for solids, but not always, because of due to crystalline structure, due to the crystalline lattice here, how strong it is, how high the energy we need to destroy it. There can be two cases, exo or endothermic. For example, I took three substances, sodium chloride with a very weak endothermic, it's very, very small endothermic effect. Potassium nitrate, it's a much bigger endothermic. Here, if we will take not potassium but ammonium nitrate, it will be even much bigger value of positive. And potassium hydroxide, it's a quite strong exothermic effect. So if you will dissolve potassium or sodium hydroxide in water, you even can feel how hot the test tube becomes. So what we can see in diagram, solubility curves illustrate that solubility of sodium chloride almost independent on temperature, a little but becomes better. So that's why sodium chloride were to be dissolved in a hot water, in a cold water, we almost see nothing, no difference, because of its so poor endothermic effect, but a little but better in a hot water. for potassium nitrate is much stronger endothermic. We will see that its solubility increases with temperature quite well. For potassium hydroxide, it decreases with temperature. And for some substances like cristallohydrates, the curve looks strange. First, its solubility increases because of losing water. And then it's for sodium sulfate times 10 molecules of water, it's a lowering because of own crystalline structure of sodium sulfate is exothermic effect of solubility. Next factor, it's a pressure effect. Pressure effect on solubility of the gases only because of, I mentioned already, water, the medium is liquid, and gas supposed to be dissolved for somehow see the pressure effect. So the pressure effect on solubility of gas is described with the Henry's law, 1803. And it states that solubility of gas in a given volume or mass of liquid is directly proportional to the pressure, partial pressure of the gas above the liquid at constant temperature. It's always so. If we need to see pressure effect, all other factors supposed to be constant. Directly proportional. Here we can write capital S as solubility is directly proportional. That means Kn times partial pressure of the gas. Or can be molarity because of its same physical meaning, that is formation of saturated solution. So to be directly proportional, there's supposed to be proportionality constant, known as Henry's constant, and it depends on all factors except pressure. So what now important to understand? That if their pressure higher 2 times, solubility increases of gas increases 2 times. So directly proportional, 3 times higher pressure, 3 times solubility higher as a result. Lowering cause opposite effect. Directly proportional. Double the concentration, we double the pressure, we double the concentration. But there are some gases not follow Henry's law. One thing you should understand that pressure always increases solubility of gases, always. Mostly directly proportional way. But there are some gases that chemically react with a solvent, they are not follow Henry's law. Their solubility higher than to be directly proportional to pressure. Higher, that means we double the concentration, the pressure, and the solubility increases not 2 but 5 times or 7 times. Why it's happened? Because of chemical reaction. Chemical reaction, factors affecting the chemical reaction rate adds to the pressure effect. And finally, chemical reaction rate, solubility becomes bigger than just because of pressure effect. What gas is not followed? As example, we can take ammonia, carbon dioxide, very good soluble, or chemically react as carbon dioxide with water. Don't follow. It still means that pressure affects their solubility by increasing, but not directly proportional. Oxygen, nitrogen follow Henry's law. Because of their solubility in water medium quite low, approximately 10 power negative 5, I mean standard temperature. What about this law we need to know? About biological, biochemical and medical application of the Henry's law. Henry's law states that solubility of the gases in liquid, in a water medium, for example, if we're talking about aqueous, directly proportional. But there we have one more factor, one more stressful factor can affect the solubility of gases. It's the presence of electrolytes. It was described this presence of electrolyte effect. It was described by Sechenov, a Russian doctor. He was a doctor and science both. And in 1859, he described that solubility of gases in liquids always decreases in the presence of electrolyte. This means that if we're interested in how oxygen, nitrogen, carbon dioxide dissolves in blood but not in a flask with the water, we will worry about both pressure effect and concentration of electrolytes. So solubility of gas in water always higher than solubility of the gas in a solution with electrolytes present. Because of here, base of the natural logarithm in power of minus Sechenev's constant, experimentally we measured, and concentration of electrolyte. That means we need to divide solubility of gas into the base of the natural logarithm in power of Sechenov constant product with concentration of electrolyte. Always, and as higher the concentration of electrolyte, as low the solubility of the gas is there. No, it can be described, it can be explained one way because of the presence of free water molecule to dissolve the substance. In electrolyte, the formation of hydrates appears. So it's mean part of the water, it reacts to cations and ions. It's not free to participate in solubility process already. So what about biological role of these both factors, Henry's law and Sechenov's law? There we can, in medical, we can deal with the two types of problems. It's a caisson disease, or other words, decompression sickness, or bend, and altitude disease. Or in some cases, we name it mountain disease. So what about caisson disease we need to know? It's a sort of pain in muscles and joints, fainting, paralysis, and even death caused by nitrogen bubbles separated from blood with a rapid change of external pressure. So what here we really observe? Due to low increasing of pressure, for deep sea divers, for example, when deep sea diver dives, higher pressure cause higher solubility of nitrogen and oxygen in blood. So, but it's not a caisson disease. Higher pressure, higher solubility, more nitrogen, more oxygen in the blood, carbon dioxide as well, and it can cause nitrogen higher concentration, can lead to some kind of disorientation maybe, but it's not cause any separation of any bubbles. But if there are deep sea divers returns rising too fast, lungs not enough time to separate extra dissolved nitrogen from the blood. Nitrogen always present in the blood being dissolved, but it was higher concentration below the sea level, and if it's rising too fast, too fast, and go back to the surface of the sea too fast, as these deep sea divers, this extra dissolved nitrogen evaporates from blood as a bubbles. These bubbles blocking blood vessels, they separate in a tissue, cause severe pain, and can lead to paralysis and death. No, it seems like blood boils. It looks like blood boils. Decompression can lead to death. No, only one way to better to prevent caisson disease. What way to, if they are deep sea diver, to first of all not stay too long. There are some safety rules below the sea, and they should ascend slow. Stop after some number of meters, not too fast. The second problem can appear, it's altitude sickness, mountain disease. It's a present as a collection of non-specific symptoms acquired at higher altitude or in lower air pressure. What important to understand here? So it never starts lower than 2,000 meters above sea level. Never stop. That means don't worry if you live on the 9th floor somewhere that you can get altitude sickness symptoms. No. Higher than 2,000 meters and 8,000 meters above sea meters, it's already deadline. So what is there happen? Concentration of oxygen in air doesn't matter if it's here or 2, 3, 5,000 meters above sea level, there will be same concentration of oxygen. The problem starts because of the lower partial pressure of the gas. According to Henry's law, we know they're directly proportional. As higher the pressure, as higher the solubility, as lower the pressure, as lower the solubility of oxygen in blood. That means same air, but less oxygen dissolves. It's a symptom of same as not enough oxygen to breathe. Hypoxia. So there are a few types of altitude sickness can be, 3 forms within. It's a mild altitude sickness known as acute mountain sickness, AMS. More often we deal with such. And it's quite similar to hangover. Headache, nausea, fatigue. Why it's happened, it's clear because of not enough oxygen, and it seems like the person should breathe more oxygen. So it's if someone feels this AMS, necessary to stop climbing, necessary to stop, not go, rest, usually for 1 day, for our body to adapt to this change and produce more red blood cells. So much worse to get high altitude pulmonary edema, HAPE. It's a higher altitude pulmonary edema, and can be higher altitude cerebral edema, HACE. They are more severe forms of AMS. So what is HAPE, pulmonary? What's happened? It means that their lungs, no, it's edema. There is a buildup of fluid. So pulmonary edema, it's a build-up of fluid within the lungs. It's mostly happen when the person climbs too quickly to altitude, and some due to this even do some various exercises, physical exercises, something. It's a stressful factor. Increase the rate of appearance of this HAPE. It leads to shortage of breath, dyspnea, coughing, fast heart rate, and decreased oxygen levels in the arteries, and can also cause fever and also leads to death finally. It's never normal to feel breathless when you are resting, when you're climbing, even if you are in Everest. Never normal, and should be taken as a sign that you have HAPE and may die soon. This is HACE, similar to HAPE, but it's build-up of fluid edema of the brain. It's a cerebral. HACE usually develops for someone already with the AMS. The swelling of the brain that led to AMS gets worse and starts to interface with the function of the brain. So we can say that HACE is a severe form of AMS. Treatment here, it's better to prevent than to treat, because of only first thing we can do when there are any first symptoms of HACE or HAPE, it's immediately necessary to stop climbing and as fast as possible go back to the normal level. So better and call for ambulance after this. So prevention is the easiest. So body should be adapted. Our body, it's amazing. It has an amazing ability to acclimatize to altitude, but it needs time. So that's why HACE can be abbreviated as a start with symbols of AMS, and necessary to stop climbing, rest till no more symptoms left. If there are still some symptoms present, so necessary to go back to the surface with a normal partial pressure of oxygen and search for doctor's help. So what then we need to know? Before to discuss very important from medical and biochemical point of view properties of solution we know as colligative properties, I want to remind you one of the property important for all of us, for everyday's life, for processes happen in our body, this property known as diffusion. It's a spontaneous process. Diffusion happens spontaneous. Spontaneous balancing of concentration of substance in a solution. So there are two sides movement. Solute from higher concentration moves to the lower concentration, and solvent from lower concentration to highest concentration. Diffusion, higher sensitive to the size of the solute particles. As big as the size, as slow the diffusion. That's why then when we discuss colloidal solutions with a diameter of solute particle more than 1 nanometer, much bigger than 1 nanometer, their diffusion happens very slow. That's why diffusion itself quite higher sensitive to the nature of substance dissolved. But the list of properties we know is colligative properties of solution not depends on nature of solute particles. It's properties of dilute solution that depends only on the number of solute particles. It can be molecules, can be ions, can be both. Number of them, that means kind of concentration important. And not nature of the solid. Also important the nature of the solvent here. But mainly we're dealing with the aqueous when we analyze colligative properties of substances dissolved. There are four colligative properties we're interested in. The first one is a lowering of the vapor pressure of the solution. That means vapor of solvent above the solution always lower than vapor of solvent above the pure solvent. All solvents, they are forming vapors. It's a natural process, spontaneous. So second colligative property is elevation of boiling point of a solution. That means solution boils higher temperature than pure solvent itself. Third one, it's a depression of freezing point of solution. Mean that solutions freezes lower temperature than pure solvent itself. And last but not least, and very important from medical and biochemical point of view, colligative properties is osmotic pressure. So let us see what there happened for each one and how mathematically we can describe behavior of solutions from colligative properties point of view. So the first one, it's a lowering of the vapor pressure of the solution. So solution above solution, always vapor present. As I told you, solvent above solvent, always present some number of solvent in the form of vapor. You can see this even if you will leave the glass with the water for example, for night, you will see condensation on the inner side of the glass. It's happened because of their vapor present. Definitely, this vapor concentration depends on temperature. But now we're talking about standard temperature, 25 Celsius, 298 Kelvins. It's present some value. Depends on solvent nature. Let us be P0. It's a standard value. They are usually tabulated. And what happened then? They are equilibrium between formation of solution and vapor. What's happened when we dissolve any substance? For example, sodium chloride. We dissolve in the water. We know that water attracts, there's a chemical reaction happened between solid and solvent. As a result of chemical reaction, some number of water molecules will be attached to the dissolved particles, it's ionic or molecular, as dipoles, and forming some hydrates. As I told you, that means things like free water concentration becomes lower in solution. And that's why, according to Le Chatelier's principle, if concentration of water in a solution, free water concentration, is lowering, equilibrium shifts to undo the stress. That means condensation of vapor is favorable here. So what we see? that our vapor tend to be condensated, and that's why less vapor concentration, that's less partial pressure of the vapor above the solution. But it's same vapor of solvent, it's not a vapor of solute and not a solution. We say in solution, meaning that it's a vapor of solvent. Mathematically, it can be described with the first Raoult's law, 1886. The vapor pressure of the solvent above the solution consists non-volatile solute, because of if they are volatile solvent like iodine, for example, it will lead to formation of own vapor and change their final result. It will be not directly proportional. But vapor pressure of the solvent above the solution consists non-volatile solute is directly proportional to the mole fraction of the solvent. Mole fraction, what is a way of expressing concentration? Mole fraction means that it's a number of moles of the, in our case it's a mole fraction of solvent, that means is equal to the number of moles of solvent over sum of number of moles of all solution components. That means if there will be one solute, there will be number of moles in denominator, number of moles of solvent plus number of moles of solute. No units for mole fraction. And this symbol, please, not X, it's symbol known as He. It's a He. Or we can write mole fraction. As you know, as you understand, if there are number of moles of one component over sum of number of moles of all others, all components. So that means it's always less than 1. Mole fraction less than 1. And that's why it's clear that vapor pressure of solvent above the solution will be lower than vapor pressure of solvent above the pure solvent. It's one of the ways to express first Raoult's law. Can be other, but this one the easiest. So what is the elevation of boiling point state? The elevation of boiling point of solution described with the second Raoult's law. And it shows that elevation of boiling point, delta Tb, here can be expressed in Celsius, can be Kelvins, doesn't matter, delta still same value, equal to the boiling point elevation constant, known also as boileroscopic constant, times molality, molar concentration, molality of the solute dissolved in this solvent. Molality, I want to remind you, it's a way of expressing concentration equal to the number of moles of solute over mass of solvent kg. It's a mole per kg. A boileroscopic or boiling point elevation constant is constant, and that's why it depends on nature of the solvent. For water, for example, it's equal to 0.516, approximately 0.52. But 3 after point, it's good and welcome. Celsius over M, where M it's a mole per kg. So delta Tb always more than 0 because of solutions boils higher temperature than pure solvent itself. For example, for water, it's 100 Celsius, but if we will dissolve the sodium chloride in it, will boil higher temperature than 100. Due to the concentration, it becomes higher and higher, till can be quite different. So, depression of freezing points states same formula, but their depression of freezing point, delta Tf, and it's this difference always we take, it's more than 0 if we take freezing point of pure solvent minus freezing point of solution. Depression of freezing point. K is a freezing point depression constant, also sometimes written as Kf. And it's a cryoscopic constant. It's tabulated also for every solvent. It's a unique value. For water, it's 1.86 Celsius per m. Again, where Cm, it's a molality. In some books, and it's acceptable in foreign to write molality just M. But M confused some because of its same symbol as a mass. But mass present as a part of the formula for molality as the number of moles. So that's why better to write or word molality or symbol CM. Do not confuse each other, your teacher and yourself. And last, but I told you not least, it's an osmotic pressure. To understand what is osmotic pressure, symbol pi here, we need to understand what is osmosis first. Let us see. Osmosis is a process of solvent flow through the semi-permeable membrane in order to equalize the concentration of solute on the two sides of that membrane. So, solvent flow from to equalize the concentration. It's familiar with them, seems same as a diffusion, and it's really truth. It's a diffusion, but diffusion through semi-permeable membrane. Only solvent molecules can pass through. So take a look what's happened. If there are no membrane between, and we have lower and higher concentration solutions, there will be two-side diffusion. From higher concentration, solute moves to the lower to dilute, and water moves to the opposite direction to dilute the higher concentration. So finally, we will get the homogeneous medium. Concentration of the dissolved substance will be same in any point of this flask. But if the membrane between, membrane only solvent molecules can pass through, but solute can't, they're still spontaneous. Our system tried to equalize the concentration to cause same concentration. So that's why solvent flows from a region with the where solvent more. That's meant from diluted part. It moves to the more concentrated solution to make both concentration equal. In such moment, osmosis stopped when concentration becomes equal. Their equilibrium reached, and now we can say what is osmotic pressure. It's a colligative properties of a solution equal to the pressure that when applied to the solution stop the osmosis. So due to osmosis, volume is changed. If we will apply pressure to stop this diffusion through membrane, to keep the level of the liquid being same as it was before the process starts to happen. So this value of osmotic pressure, this is pi value. So how this mathematically can be expressed? It's expressed with the Van 't Hoff's law. Pi osmotic pressure equal to the mathematical product of concentration, molarity, molar concentration of the solute dissolved in exact volume of liquid, gas constant, which is 8.31 or no 8.31 enough, joule per mole Kelvin, and temperature should be Kelvin scale. One of the more often mistake happen when you determine osmotic pressure to predict can solution be used for intravenous feeding or not. It's the thing you not convert Celsius into Kelvin scale, and that's why osmotic pressure becomes wrong, and solution can leads to death of the patient if you will use wrong concentration, wrong osmotic pressure solution. So what here we see that osmotic pressure and concentration are directly proportional. So, and again, if diffusion itself depends on nature of the substance dissolved, for osmotic pressure, for osmosis, only solvent important because of solute can't pass through membrane. For osmotic pressure, important the number of solute particle. That means concentration if we're dealing with non-electrolyte. This formula is correct for non-electrolyte. So how we can apply this information in medicine? The osmotic pressure of the blood is strict interval between 740 and 800 kilopascal. This value you must memorize. 770, 770, it's an average. But within this interval, it's a normal osmotic pressure of the blood. That means there will be no change in shape with the red blood cell if we will place a solution with this red blood cell in solution with the same osmotic pressure from 740 to 800. Solution with the same osmotic pressure as blood, known as isotonic to blood solutions. And there are no change in shape, water in, water out. It's a diffusion through membrane, semi-permeable membrane. If their solution has a lower concentration than our concentration of the electrolytes, non-electrolyte inside the red blood cells, that means solution has lower osmotic pressure than blood. Such solution known as hypotonic solution, and their lysis or hemolysis appears. What's mean? Water in and leads to the red blood cell burst. Hypertonic solution has higher osmotic pressure than blood, and that's why water leaves the red blood cell, leads to shrinkage of the red blood cell, and it's known as cremation or plasmolysis if we deal with blood. How it look like in a picture more clear. So water out, it's a hypertonic shrinkage. It can't carry oxygen anymore. Isotonic, no change in shape, and hypotonic, water in till red blood cell burst. The worst case, because of if hypertonic solution somehow we can apply little amount of hypertonic injection of hypertonic we applied in medicine, it even can cause formation of red blood cell more, it stimulate erythropoiesis. Hypotonic intravenous, never. And what necessary to know about all of these factors important for electrolytes and non-electrolyte both. But we know the difference, that if we use non-electrolyte, the concentration equal to number of particles. So that's why first, second, Raoult's law, Van Hoff's law, there will be formula according to what I mentioned above. But if the electrolyte is present, due to its strong or weak, it can dissociate completely, can dissociate partially. The value, the amount of particles really formed after electrolyte dissolved, described with a Van Hoff's factor, isotonic coefficient. It shows the ratio between real number of particles present after the substance dissolved to the number of particles supposed to be according to the concentration. So that's why when we deal with non-electrolyte, there are no dissociation, I equal to 1, and that's why we never mention even isotonic coefficient for non-electrolytes. So if we will determine osmotic pressure of glucose, leads glucose solution, there will be just CRT without any Van Hoff's factor, because if we know glucose is non-electrolyte. But if there will be electrolytes, strong electrolytes. We know all soluble salts are strong electrolytes. That's why we know they dissociate completely. Isotonic coefficient, Van Hoff's factor, we measure experimental way. Why? It depends on alpha. Alpha is dissociation degree. And as I hope you know that dissociation degree for electrolytes, for electrolyte to be strong, enough to be more than 30%. How it's possible? 100% dissociation happen always if electrolyte is strong, but somehow when we measure, alpha becomes less than 100. Why? Because of attraction with the water, because of formation of hydrates. That's why experimental value measured conductivity. What is there we measured? We dip electrodes and cations moves to one direction, anions to other, due to the passing through each other, the inter-ionic interactions. Water also not allow them to move too fast. So that's why experimental value far from 100 and can be quite far. As higher the concentration of electrolyte, as higher the inter-ionic interaction, and that's why isotonic coefficient will be for sodium chloride, for example, equal to 2. Exact 2, only if there will be ideal solution. Ideal solution, it's a solution with no inter-ionic interaction. Every ion, every molecule, independent way seems like present and not affect others. It's same as ideal gas never happened. But as more diluted the solution, as more perfect I to be 2. No? So if there will be concentration 0.01, there I almost 2 because of its 1.98. If there are 1 mole per liter concentration, it's already 1.78. No? So approximately 2. But if we need to know exact value, only experimental way. So I shows a number of ions formed due to dissociation, if it dissociate completely. So 2 ions, that means I approximately equal to 2. If the potassium sulfate, for example, their I approximately equal to 3, as there's 3 ions formed due to dissociation. For strong electrolyte, we accept they dissociate completely, and that's why I can be predicted approximately. If we need to determine the value exact without any approximate idea, we need to take experimental values measured by someone, or we can measure ourselves. So that's why if there we have some correction coefficient, 1/2 factor, it should be mentioned in the formula of the second Raoult's law and 1/2 law. So what there we have? Elevation of boiling point for electrolytes higher and approximately 2-3 times higher than elevation of boiling point for a non-electrolyte with the same concentration. Freezing point same, 2-3 times higher, no, that means lower freezing point than for such solution with the same concentration, same molarity for non-electrolyte. This is important from scientific point of view, elevation of point, depression of freezing, because of we have no temperature changes in our body, but osmotic pressure, this value we need to know quite well, quite close to be perfect value, to make conclusion about application of this solution for intravenous feeding. If we applied 1-2 milliliters, we will not lead, even hypertonic will not lead to death. But, and we even use in medicine, as I told you, injection of hypertonic solutions. But if we deal with 100 ml for intravenous, if we will use not tonic to blood, the patient will die. So that's why it's very important to understand, is it electrolyte you use intravenous or not? Because if we can use both, sodium chloride we know, we can deal with the calcium chloride, we can deal with magnesium sulfate intravenous, but glucose as well. And some medicines we can deal with, they are non-electrolyte nature, and their osmotic pressure to determine, we use CRT for sodium chloride, magnesium sulfate, calcium chloride. We need to determine, we need to write dissociation to be sure how many ions they are in solution present. So I think enough for today. I think, yeah. So if you have any questions, you can ask for. If you do have any questions. If not, the lecture is over for today. About when will be next lectures, for now, it's a second lecture hall. Maybe just psychology will be 19th, but I will tell you this before the lecture. Biology and chemistry lecture hall number 2. Till New Year, we have lectures there. After New Year, we'll see. Maybe there will be some changes because of, for some students, their second semester will start. We still have till the end of the February, we have first semester. Only last week of February, there will be credit week for you to complete all your reworks and get the highest points can be in every subject. Okay, if everything fine, I was really happy to see that a lot of students, let us say, more than 50% started at time to attend, but there are some still late. I hope next time it will not happen. Okay, goodbye. My group, see you class time. Don't forget, you need to prepare your home task to submit. Okay, goodbye. See you next week. My group, see you today.